Okay, hello, here we are again. This time we're looking at equations of planes and equations of lines using dot products and pictures. Okay, so first of all, let's do planes. So a plane, I don't know, P, we don't have to give it a name, but we can give it a name, is a flat surface. It's a linear surface. And so it can always be described by one linear equation when it's a plane in R3. Incidentally, if you're in R4 and you had a two-dimensional plane in R4, you would need two equations to describe it. The one equation sort of knocks out one of the four dimensions, and the second equation knocks out a second dimension. 4 minus 2 is then 2, which is the dimension of a plane, is a two-dimensional plane. But anyway, so if we want a two-dimensional plane in R3, we only need to knock out one of the dimensions with one equation. And so here's what that equation can look like. This is the most general form it can be if it's going to be a linear equation, which would give you a flat surface. So yeah, so for some fixed numbers n1, n2, n3, and some fixed number c, I just called them that n for normal and c for constant, but it doesn't, you can call it whatever you want. This is just the dot product of that vector n with the variable vector x. And so I just sort of wrote this in two different ways so you could see different ways. And visually, n is the normal vector of the plane. It gives its tilt. And c shifts the plane off the origin. That's what we see here. So like if c is 0, if this is the equation of the plane, then x equals 0, 0, 0 is always a solution. So like here, this is the point 0, 0, 0. It's also called the origin. The origin is the point 0, 0, 0, 0, 0, 0, 0, whatever dimension is the number of zeros. And then if we want to shift it off the origin, so we take that same normal vector, there it is, there it is, there it is. Let's say that's all the same vector. Well, if we said the n dot x equal to 3, then we're shifting the plane sort of in the direction of n, coming off the origin this way. Whereas if we say n dot x equal to negative 5, then we're shifting it in the opposite direction of n in some way. And we're not actually shifting it by negative 5 units. If n was a unit vector, and we know how to make it a unit vector, so you can always do this if you want. If n was a unit vector, then this equation would be shifting it off the origin exactly by the length 5. And this would be shifting it off the origin by length 3. But for general vectors, there's like, sort of a messing, it gets messed up a little bit, but still the direction positive or negative works. Now if we change n, and instead change it to some other vector v, which we could also call n, because now this vector v is going to be the normal vector to this some different plane. This plane has a different tilt than our other plane. And so the vector v or n or whatever you call it, that gives sort of the tilt of the plane. This one, since we set it to be 0, is passing through the origin. And yeah, I wrote it out in full coordinate form compared to this sort of abbreviated version where we've hidden all this linear combination in the dot product symbol. Okay. Great, so lines in the plane are very similar. They're also specified by one equation, this time in two variables. And I wrote it in two ways, sort of a more detailed form, and then a shorthand where we've put some of the details into this dot product notation. Okay, so same thing, like if this was our normal vector, then n dot x equal root 2 moves it some direction along the direction of n, off the origin. And n dot x equals negative pi, just some negative, like negative 5, negative 7, negative pi, moves it in the opposite direction to n and shifts it off the origin. Whereas n dot x equals 0 would then mean it passes right through the origin. Okay? And if we change n, and instead we had a different n, like pointing off in negative 1, 1 direction, then the tilt of our line is different. The slope of our line is different. Okay, so that is, that's it.